picture. Right from? Recognize?
Yeah.
Weizmann Institute. Right.
It's on the wall over there.
I was there. What?
It was on the wall. It's your task for the break to find this on the wall.
On the wall. Are there pictures of all programs for different programs?
I don't know if all of them, but the nice
But this one. So it was a summer program, an excellent summer program on high-dimensional expanders. And the Irit will tell us about these high-dimensional expanders and multiplication programs. Thank you.
Thank you. Okay. So hi, everyone. Thanks for the invitation. I'm so happy to be here. Okay, so this is joint work with Siki Liu, who was a Berkeley grad student and is now a postdoc at DIMAX, and Rachel, who was here until yesterday, and she's an MIT grad student. They were both visiting me, and we had a really nice time. So let me tell you, start by saying what multiplication codes are. So if C is some error correcting code, and I decided to skip the Alice and Bob story, then we say it's an addition code. If you have two strings A and B, then the sum is also in the code, right? So if it's a linear code, you always have this addition property. And multiplication is the same, but with multiplication. So if you have two codes C1, C2, and you take the coordinate-wise product, so this thing says that the ith coordinate of A star B is AI times BI. And by the way, we saw this in yesterday's afternoon talk and in various other talks throughout the week. We already encountered this multiplication property, so you know it appears here and there, and it's interesting. So what does this really mean? It means that these code words allow you to do some kind of operation under the hood, like under the encoding. You don't need to decode to do this. Okay. And what are examples of codes that have this property? Well, read Solomon codes. They are good examples because if you have a degree D1 polynomial and another degree D2 polynomial, the pointwise product is degree D1 plus D2. So it's not that you stay inside the code, but you go into some slightly larger code. And of course, all these other evaluation codes that we learned about yesterday, Reed-Muller and algebraic geometry codes, they all have this property. So who wants multiplication codes? So one application, end-to-end application that Yuval was telling me about yesterday is for secret sharing. I'll tell you about it in a second, just to say that really it's, you encode data for various reasons, and sometimes you want to do computation on the data, so it's natural to want to do this kind of thing. So let me tell you how secret sharing uses, not secret sharing per se, but taking secret sharing one step up and doing some kind of secure computation. So suppose you have a secret, you add some random bits, and then you take this string and you encode it in some systematic code. So now the whole thing is a code word. And in secret sharing, what you do is you take parts of the encoding part without the systematic part, and you distribute it to various servers. And now each server separately, by the distance properties of the code, it cannot know anything, has no knowledge about the secret, but together they can reconstruct it. And this is secret sharing. Now, if you have two secrets, suppose you now want to compute something on these two secrets. Suppose S1 and S2 are indicators of a set. So S1 is some 0-1 string and S2 is some other 0-1 string. You do this secret sharing for each one of them, and now each server gets two parts. Now the servers can do the pointwise multiplication of these two strings, and what they will get is shares of this code word, which is contains in it the secret, the set intersection of S1 and S2. I don't know if I explained it very well, but I hope you understood, because it's, even if I didn't do it well, I think it's pretty simple to see. So you see how this multiplication thing, there is some homomorphic thing going on, and it's nice. Okay, so you don't only want to do set intersection, you want to do other computations and so on. And for me, really, if you know me, you know that my motivation wasn't from secret sharing necessarily. It was from something to do with constructing PCPs. So I'll tell you a little bit about it. Maybe I should use this. Yeah. Okay, so error correcting codes make data more robust, and PCPs, you can think of them as making proofs more robust or making computation more robust, more resilient to errors. And of course, it's not only that it's more resilient to errors, you must also be able to check it by looking at a very small part, a random tester. So what is the coding theoretic analog of PCP? This is called the locally testable code. It's an error correcting code that you can locally test if your string is in the code or not. Okay, so LTCs, these are codes with good testers. I'm not going to define it formally, but just know that it's the kind of codes that can be defined by the parity check matrix, and they have this property that if you have a string that violates only a small part of the parity checks, then it necessarily means it's close to the code. And that's not the property of general LDPC codes, for example. So these are special codes that are testable. And it used to be that the only constructions we knew of LTCs came together with constructions of PCPs. But this changed already several years ago, and it was still not known whether LTCs are codes that can have the same kind of properties as normal codes. Can they have good rate and good distance? And this was resolved recently, and now we know that we can have LTCs that have constant rate, constant distance, and testable with constant locality. So now we know that LTCs are like all normal nice codes that have only linear overhead. The way these codes are constructed, it's very far from PCPs. The construction is kind of using these nice high-dimensional expanding structures, which I think Prahlad talked about it in the bootcamp, and I'm not going to talk about it too much, just to say that there is some component there that we think of as a high-dimensional expander. But today I'll show a slightly different such object. Okay, so we have these LTCs, so it's natural to ask, okay, what about elevating it to a PCP? Can we construct PCPs using similar methods? And okay, we don't know how to do it. But one small step would be to get these codes to have some features that you need for a PCP construction. You know, the kind of the codes that are the best in almost every respect you look are the polynomial codes. And so, you know, we look at them and we try to see if we can get properties that are like what they have. For example, multiplication. Another thing that you would really need here is to be able to do some kind of sum check protocol. But I'm not talking about it today. So just to summarize this slide, the vague motivation for me was to get LTCs like the ones we already have, but that have PCP-like features. Okay. So now let's start to describe the construction. Let me start by just talking about expander codes. The day before yesterday, we heard a couple of really nice talks involving these objects, but I'll describe it anyway. So we have here a family of deregular, deregular graphs. So the family D stays fixed and the number of vertices goes to infinity. And we have some fixed base code on D bits, so just a constant size base code. And together these two you make a code out of them by looking what is the code space. It's all labelings of the edges, so just functions from the edges to some alphabet, say 0, 1, such that around every vertex, if you look at the bits just touching the vertex, these bits are in the local code. Okay, so I'm imagining most of us know about expander codes. So what are the features of expander codes? Firstly, you can quite nicely prove that they have linear distance as long as the distance of the local code, delta 0, is bigger than the spectral expansion of the graph. So if the graph is a good expander, you get a distance that's roughly delta 0 squared. Just roughly, why would this ensure distance? If you look at some code word and there is some non-zero bit, then around this vertex, you should have delta 0 fraction of non-zero bits. And then you look at each one of these endpoints, and it itself should have more non-zero bits. And if the graph is an expander, this will propagate. Yeah. So you can prove distance quite easily. These codes are a low-density parity check just because we think of graphs that are d regular and d is a constant, so all the parity checks have width no more than d. By the way, they're not usually locally testable codes. So to be locally testable code, it means that if you have some string that violates, say, just one or two constraints, it must be very close to the code. But in these codes, you can have strings that are very far from the code and only violate one or two constraints. You can think about it. Okay, what about the rate of these codes? This is going to be very interesting for this talk. Really caring about the rate. So the way we prove rate for these codes is just by counting constraints. We see how many degrees of freedom we have. We have E edges, so that's the number. And we see how many linear constraints we have. And this is for every vertex, we have some number of constraints for C0. And if the total number of constraints is smaller than the total number of degrees of freedom, we have rate. And this works out exactly when the local rate is above a half. Okay, and our rate is going to be above, at least this number. I'm talking about relative rate, so this is a number between 0 and 1. Okay, when R0 is less than a half, this is negative, so I don't get anything. But the rate, this is a lower bound on the rate. The rate can actually maybe be higher. Okay, and what I'm interested in is what happens if I'm going to put a local code here whose rate is smaller than 1/2. And why am I going to do that? Can anyone guess? Why do I care so much about having rate less than 1/2? Multiplication. Right, so a multiplication code, if it has rate above 1/2, it's very likely that when you multiply, you'll fill up the entire space. So if you want a multiplication code, the rate needs to be less than 1/2. So that's why this is going to be kind of crucial. And so here's an example, tensor codes. One of the speakers, I think, actually mentioned this. Tensor codes can be viewed as expander codes on the complete graph. The complete graph is an expander. It's not constant degree, but it's an expander. And for tensor codes, the local code is really the code that you're tensoring. And the rate is the rate squared, or maybe R1 times R2. Anyway, the rate is always positive as long as these guys are positive, no matter if they're above a half or below a half. So there are examples where the rate is small and yet the code has positive distance. And I think kind of a very nice question is to find such things. Okay, now what about multiplication for expander codes? So what is a condition for an expander code to have the multiplication property? Well, if I have a string that's in the code, it means that locally, every local view is in the small code. I have another string that's also the same. When I multiply them pointwise, I multiply the local views pointwise. So if the local code was multiplication, the entire code will have this property. Okay, so here is my open question that I don't know how to solve, but I haven't spent years solving it. So I urge you to think about it, and I'm happy to talk about it if anyone cares about this. So here's the question. Fix some prime p, like 17, or some fixed number. And then we're interested in finding an infinite family of p-regular expander graphs. These are Gn. And then we will look at the expander codes where the local code is going to be Reed-Solomon. So we're just the alphabet is not binary. It's going to be, FP. But we only want local strings that the local view makes a polynomial of degree at most r, for r some parameter. Now, if r is above p over 2, we already know that this has positive rate. So I'm interested in r being below p over 2. Okay? Even if it's 0.49 times p, we'll already get a multiplication code, right? Because the product of two polynomials of this degree is a polynomial of degree seriously less than p, like 0.98, right? So that would be great. Okay, so this is a.
The local codes have to be read Solomon. Can we know if there are other codes that can do this?
Okay, great question. So here, when you ask an open question, you want to make it specific, maybe, I guess. So I said read Solomon because it has multiplication. But the question would be interesting even for other codes. If you can find interesting codes that have small rate and yet the whole thing is has positive rate, that would be great. Okay, so really, in this talk, I'm going to describe some code that to some extent, some weak extent, manages to make progress against this constraint counting barrier, to circumvent this, okay? So how can you imagine doing that? Okay, you build some expander code. How would you show that the rate is bigger than what you get from the constraint counting? Okay, one natural way to do it is by showing code words. You actually show a bunch of linearly dependent code words, and this gives you a bound on the rate. So the way we're going to do it here is by embedding some other space, some other code into the space of code words in our expander code, and that's how we'll show that the code actually has some rate. And the space we're going to use is going to be polynomials. Okay, so I had two ways to make this talk. One of them is to continue with expander codes and just talk about how to do it. And the problem is it would take me longer to prepare, and it's not what's in the paper. But it would have been possible, I think. But instead, I chose to take the easier route, which is to follow the paper. So in the paper, we did what I just said in this previous slide. But we didn't do it on expander codes. We looked at the higher dimensional codes because we also wanted to have the local testability property. So we were kind of, we knew how to do it for the higher dimensional thing. So it's more complicated. Maybe it's less clean to understand. But it's all the same ideas. So what is that? So let me take the opportunity to describe it. So what is a high dimensional expander code? So really you have a graph, vertices and edges, and you also have triangles. That's all. You can have higher dimensional faces, but not for now, not for this talk. Okay, so you have these vertices, edges, and triangles. And now to construct the code, previously we put the bits, like our code word were bits on the edges. Now we're going to put the bits on the triangles. That's the same thing, just one level up. Okay. And previously, for every vertex, we said that the local view of the vertex, all the edges touching it, should have, should be in the local code. So now we're going to put all the triangles touching an edge. So maybe I should draw this. I guess in this graph, we have triangles, and maybe there's, a few triangles touching a specific edge, and then, I don't know, some. So for this edge, there's 4 triangles touching it, and there's some bits written on these triangles, 1, 0, 0, 1. So you want this local view to belong to the local code. It's very similar to the expander code case. Okay, so that takes care of these 2 bullets. What about, what do the vertices do? So I'm not going to get into it. The reason to move everything 1 dimension up is that now the vertices can do something and add redundancy among the constraints on the codes. But this is good for proving local testability, and I'm not going to get into it in this talk. Okay, so now how do you analyze such codes? So the distance of the code follows from expansion, just like we did it for expander codes. Local testability follows from the vertex part, which I'm not talking about. And what about rate? So for the same kind of arguments that we had before, if the local rate is big enough, now it has to be 2/3, not 1/2, because every bit, every triangle participates in 3 constraints, not in 2. So if it's above 2/3, you get positive rate. Okay, so you can build LDPC codes on high dimensional expanders. It's not a problem. But of course, just to say, but of course, we want multiplication codes. So we want our local codes to be such that this rate is less than a half. Not only it's not more than 2/3, it's less than a half. Okay. So as we said, our approach for circumventing the constraint counting is to embed Reed-Muller codes into our high-dimensional expander codes. Okay, so for me, for this talk, for this talk, Reed-Muller codes usually, or this is what it is, it's all the functions of some total degree at most d.
By that you mean like in the analysis, right? So that's the code.
Well, yeah, just in the analysis, yes, to prove rate. Thanks. Yeah, okay, so Reed-Muller code, it's all functions of some degree bound below d. But it's also okay to look at this code, which is all functions such that when you restrict them to any affine line, you get degree at most d. I mean, this code can even be a bit bigger. That's fine for us. But I'm not going to distinguish between the two. Okay, I have a picture. What is this picture? Okay, so here you see the Reed-Muller code in a geometric view. Okay, you have some vector space. And for every line, what you see on the line should be low degree. And here you have what is sometimes called the Tanner factor graph. So the bits of the code are on the left. It's not bits, it's elements in FQ, FP, I think. And here you have a vertex for every line, and this vertex requires that the local view that it sees is a low degree function. Okay. So what will our codes be? Our codes will just be this. They're going to be some careful selection of a subset of the vertices here, and a subset of the vertices here. And the induced graph will be the Tanner graph of our code. Okay, so all I need to tell you is which subsets. Okay, but this is going to be the idea. We're going to basically, what does it mean a subset of the vertices here? It means we take not the entire vector space, but some variety inside of it. And then not all of the lines, some of them won't even be inside my variety. But enough lines will be inside, which we're going to take here. So that's going to be the code. Okay. So here is a theorem. There is some construction, which I'll show you, of triangle complexes. So think graphs that have triangles. So it's some infinite construction of expander graphs with triangles, such that for each one of them, so let X be one of these guys, you have a one-to-one matching between the triangles of this graph and the points in some vector space Fn, such that you don't get all of Fn, but you get a constant power. So I'm assuming F is Fp, sorry. Okay, so instead of being all of Fn, I get like p to the n to the c for some c less than 1. Okay, and more interesting, I mean, this part you can always do, right? You can take any graph, just arbitrarily map each one of its triangles to some point in some space. But the interesting thing here is that for every edge, if you look at the triangles touching this edge, the points that they map to are going to be an affine line. Okay, so this makes the embedding non-trivial, like interesting. And also, for every vertex in this embedding, and I'll show it, the triangles touching this vertex, so how many will I have? I'll have p to the 3 triangles, and they're actually going to be like a copy of f to the 3 inside f to the n. And it's going to be tiled with some number of lines. Okay, we'll see it. Okay, so I want to slowly kind of build up to showing this. To show this, so I need to show you a family of two-dimensional graphs. I'll start by just normal graphs. So let me show you first the construction of a graph based on cosets of subgroups. So some of you have seen this, and this is going to be familiar, but if you haven't seen this, I'm going to go a bit slow. Okay, so suppose you have two subgroups, H1 and H2, and you look at the span of the two of them together. A coset graph is a bipartite graph between the cosets of H1, the cosets of H2, where you connect two cosets if they intersect. There's a different way of thinking about it. And this different way, I like it. It's you start with G edges that are kind of separate, they don't touch each other, just G copies of a single edge. And then you start to glue them together. So you glue different endpoints if they belong to the same coset. So let's look at an example. Here I'm going to look at the group Zn times 0, so it's basically Zn. And the second group is going to be 0 times Zn, so again, just Zn. And the group that they span is just Zn times Zn. Okay, so H1 and H2 are subgroups of G, like we need. And now, what does the coset graph look like? So I'm doing Z3 here. So I have 9 edges. And I label each edge by an element of G, so Z3 times Z3. So 0, 0, 0, 1, all the way up to 2, 2. And now I'm going to look at the left-hand vertices and glue them according to cosets of H2. And the right-hand vertices, I'm going to glue them according to cosets of H1. So see, cosets of H2 is just, you keep this coordinate the same, and you bunch all these together. So you see these 3 vertices become one vertex. And for H1, you look at the other coordinates. So you go 0, 0, 1, 0, and 2, 0 are bunched together. Do you see this? Okay. So what did we get? We got a K3, 3. We have 3 vertices here, and all the edges. That's what we happen to get in this construction. So K3, 3 can be viewed as a coset graph with these subsets, with these subgroups. Okay, here's a more interesting choice of subgroups. So now I'm going to choose subgroups of matrices. So here, H1 are all the matrices with 1s on the diagonal and 0s everywhere except A over here. Now this subgroup, when you multiply 2 of these guys together, as you see here, what you get is just that the A's add up. Okay, so although it looks like a group of matrices, really it's just ZP or FP. Okay, it's an abelian group, very simple. So this H1 is really just a copy of FP with plus. And similarly, H2. H2, the non-zero guy is here, but when you multiply, you get addition. Okay, it's nice that you can get addition while doing matrix multiplication. Right? Okay, so that's H2, also just a abelian copy of FP. But the product is now more interesting than the earlier we had just product of two abelian groups. The product here, if you multiply something with A and something with B, you get also A times B here. Okay, so the group that you get doesn't have size P squared, it actually has size P to the 3. So that's what these groups are. So now what does the coset graph look like? So this is wrong, actually. Is it wrong? It's P3 edges. Okay, ignore it. Okay. So this is a picture. Okay. What does the coset graph look like? You have the cosets of H1 on one side and the cosets of H2 on the other side. And you're going to have an edge for every element of the group. Now, the group, remember, was matrices with 3 non-zero entries. So the group had size P cubed. So we're going to have P cubed edges here. What we got is a bipartite graph with P cubed edges. And what is the regularity? So remember, the way we got this graph was by bunching things together. And we bunched H2 things together. So the degree here is like the size of H2. So it's P regular. And the number of cosets is P squared. So you have P squared vertices here, each one of degree P, and the same on the other side. That's our graph. And turns out it's a very good expander. And we can make it into a code. How will we make it into a code? We want to introduce Reed-Solomon constraints on the around every vertex. Just an expander code. Now, sometimes we ignore this issue, but it's always there. When you define an expander code, it's not enough to say, oh, the local view needs to be in some local code. You also need to order the edges somehow. You need to tell me how to order it. And here I'm not going to do some arbitrary ordering because it won't be in my favor. I actually want to do this ordering by looking at this algebraic construction. So remember, what were these G's? They were matrices with 3 non-trivial coordinates. So I'm going to use this to order the edges properly and get the code. Okay, so the edges were all the matrices with ABC, ACB, okay? It naturally maps to F to the 3. Oh, and the code, it's written down here. It's all functions on F to the 3, functions on ABC, so that these two constraints happen. So if I kind of look into the definition and unravel what it means to be in a coset of H1, I will get this definition that for every BC, when you range over this field element, you should have the degree be less than D. And similarly, from the other side, it looks a bit less clean, but it's again just a line for every, I don't know, ABC, but there's only two parameters that really change. This should be, this is some kind of line, and it should have degree at most D. So this is what you get. You get some kind of code. And now it turns out, I learned about this from Gilles after we wrote the paper, that this code was already studied. It was studied by, I don't know how many years ago, maybe 10 years ago, or more than that. Okay, so unfortunately for us, we didn't know that. And we worked hard to do things that they did much more elegantly. But anyway, this code was studied, and proving distance is easy based on the expansion. Analyzing the rate is more tricky, and the rate of this code is the rate cubed. So if you look at the local rate as some kind of fraction d over p, then the rate of the code is roughly this rate cubed. What does this mean? It means that if the rate goes to 0, like 0.2, you still have positive rate here, which is kind of what we want. So that's really cool. And of course, as I told you, we were also very interested in local testability. So you also want to prove something about that, but I'm not talking about it today. Yeah, I have no idea. I mean, it's F3, right? So I don't know.
Based on the parameters, it looks like this graph is lines versus points, incidence.
It's not, is it? I forgot. Is that true?
It looks like, I mean, just p squared, p cube is what happens.
Oh, you're right. You're right. It might be. Now I don't remember if it is or it isn't, but it could be. Could be. Yeah. It is? Okay, thanks. Okay. Okay. What else did I say? Okay, so far we talked just about graphs. Oh, and just to say, so that was really nice, but the number of vertices is like p squared, and the regularity is p, so we are not getting a constant degree family. So now we move to something that does give us a constant degree family. So these are a slight variant of coset complexes constructed by Kaufman and Oppenheim. And this was a beautiful construction of a high-dimensional expander that you can understand everything by elementary considerations. It's really nice. So let me describe it to you. You have three subgroups very similar to what we had before. Previously, I just looked at these two. There's a third one with the non-zero coordinate here. And now you define three other subgroups. So K12 is the span of H1 and H2. And we saw that. Previously, we called it G. It was just this ABC thing. I'm ignoring the blue stuff. And similarly, K13 is the span of H1 and H3. So you get these non-trivial things in various coordinates. And our coset complex will be based on the cosets of the K subgroups. Now, to make this kind of number of vertices grow while P stays fixed, we're going to take these matrices not over the field, but over the polynomial ring. So T is this indeterminant of the polynomial, and we're going to have some irreducible with degree n, where n goes to infinity, and all these matrix multiplication will be modulo this irreducible. Okay, so the field is actually going to be much larger than Fp. It's really like F to P to the n. Okay, so it turns out that the span of these subgroups, these three or those three, it's the same, is just all matrices over this polynomial ring with determinant 1. So you need some condition, some division condition. Essentially, this is the group. So really what's going on is you have now a group, a collection of matrices. And of course, each matrix, you can view it, you just open it to a 9-coordinate vector. And each coordinate here being an element of f p to the n is an n-bit, not n-bit, n-length vector over fp. So you get every matrix naturally can be seen as an element in fp to the 9n, right? So the group kind of naturally embeds as a set inside f to the 9n. And I'm saying it's a variety because there is some polynomial equation that says the determinant needs to be 1. Okay. So this is our group. And now we build the coset complex. I didn't tell you the general recipe how to do a coset complex, but you can see here, you look at cosets of the three, the kij's. I'm sorry, I wrote 1, 2, 3. I should have written 1, 2, 2, 3, and 1, 3. And then the way these things works, the edges themselves are cosets of the hi's, and the triangles are just elements of G. So I tried to depict it. So what do I have here? I have a tripartite graph. This part are all the cosets of K2. This part are all the cosets of K3. Okay, I renumbered them, K1, K2, K3. And this part are the cosets of K1. And I connect two cosets if they have some non-trivial intersection. Okay, just some element of the group participates in both of them. And I connect three cosets if they have some non-trivial intersection. And it's always going to be a single group element. And the way this was set up, you will have exactly one triangle for every group element. This is how this complex turns out to be. So you get a tripartite graph. The triangles are exactly in one-to-one correspondence with the group, which, as we said, is roughly, I didn't say, it's embedded in f to the 9, but the fact that you want the determinant to be 1 means you lose one field element, so you get f to the 8. And it has some other very nice property, which is this. If you look at the triangles that touch a specific edge, and you kind of unravel what it means to be triangles that touch one specific edge, you will see that these triangles, they all sit on some coset of H1, for example, which is this abelian group. So it exactly maps into a line. Okay, so the degree, I mean, the number of triangles touching an edge is P, so that's already a hint. But not only it's P triangles, it's actually points on a line. And the triangles around the vertex are now a copy of the graph we saw before. So it's you have it's the link of the vertex. It has p to the 3 edges and 2p squared vertices. Okay. So there is this geometric view where the purple box is f to the 9n. This yellow blob is supposed to be all the points that come from matrices with determinant 1. And I don't know if you see, there's these green lines. So these are affine lines in this space that happen to be kind of contained in this variety. And notice that every triangle has 3 edges, right? So every triangle participates, each edge is a line. So every triangle participates in 3 lines. So it means that every point here has 3 lines from the special collection of lines that we have that go through it. Okay. So to summarize, what we have here, together with this embedding, we specified a set of points in this vector space and a set of lines in this vector space so that every point participates in 3 lines. And there is some expansion stuff going on. Okay. Yeah. Okay. Now that we defined the complex and how it maps into the vector space f to the 9n, it's immediate to define the code, right? You just require functions on this yellow blob that the restriction to each one of the lines is a degree such and such. Okay, so if you want to view it as a high-dimensional expander code, you say that around every edge, the local views are in the Reed-Solomon code. But I think it's cleaner to see it here. Okay. Interesting point, or maybe it's not interesting, I don't know. If you look at all the triangles touching a vertex, you also get a code. You kind of get a local view of this global code, and it happens to be the code we discussed earlier with the lines versus points thing. Okay, I guess this is my last slide, or one before last. So what do we have? We have a new family of LDPC codes. I'm highlighting the degree restriction, but really it depends on D and P and N. Depends really even maybe on the irreducible polynomial, I don't know. If the degree we choose is bigger than 2/3 times the field size, we get linear rate. We saw that. If the degree is smaller, we still get something, right? Because every Reed-Muller code word, when you restrict it to the yellow variety, it's still something. It still has degree D in every line. So you get some non-trivial bound on the dimension, but I mean, this dimension is going to be non-linear even when D is large. So clearly, this lower bound is not correct always. And maybe some more clever arguments can be used to show that it's much higher than we think. That's the rate. The distance is very easy. You use expansion, and as long as the degree is slightly bigger than square root p, you get good distance. Local testability, I didn't cover today, but we showed that when d is less than quarter p, you get local testability, and this is by argument similar to Polishuk-Spielman adapted to this code. For larger d, the local code is no longer locally testable. This, I think, Rachel and Louis proved recently. But it doesn't mean that the global code is not locally testable. To prove local testability, we have some kind of template where you prove it locally on the vertices, and then you deduce it globally. Now we know that for larger d, locally it's not true, but we don't know, as far as I know, maybe you guys know, a counterexample for the global local testability. And we have multiplication as long as this makes sense, as long as d1 plus d2 is less than p. So these are always going to be multiplication codes. And another nice property is that this whole construction is very symmetric. The group G acts on it. And the way it acts on the coordinates of the code is linearly, so it also acts on the code itself, because the Reed-Solomon has linear invariance. So it's a nice symmetric code. Yeah, that's it. So let me summarize. We have a new family of codes. I didn't talk at all about the square codes, but it's analogous in the sense that the bits are now in the triangles and not the squares. We have some bounds on the rate, but a lot of it is not, I don't think it's optimal. It's locally testable for some parameters, and we saw the other properties. One more thing that I want to say, and the way you did it for triangles, you can do it for higher dimensions. And it's also natural to use this to define a quantum code, which I didn't say anything about that. So you can define the code, but understanding if it has any distance, it would have been easy to show if we knew how to prove local testability, but since I don't think local testability is true, I don't know anything about the quantum distance. Okay, that's it.
Any questions?
So for the quantum code, where are the x and z checks?
Yeah, so for the way to make it into a quantum code is that you think of putting the bits not on the triangles, but like on the edges. And then from the vertices, you do the z checks, and from the triangles, you do the x checks.
And the triangles, what's the local code? Just a-
So I would still put Reed-Solomon codes. Their duals are also Reed-Solomon codes. But of course, these are not, they don't have the correct robustness that we know how to utilize. So.
And we just want to know what's the connection between the construction you showed us and the open problem you posed at the beginning of the talk.
Ah,
I mean, why does it not solve the open problem?
It doesn't. I wish it did. It's a family of expander codes. The local codes have small rates. So in that sense, it's related to the question. But the thing I would love to prove is that the rate is positive, it's linear. And here the rate is only like some constant power of the block length. So
So
it's
that's
not linear. Yeah, that's the main thing. And Yuval promised me that if we get linear, we will have all kinds of applications and stuff. So, yeah.
good. Any more questions? Okay, so let's thank the speaker again.